In this video, we will talk about how to actually evaluate a machine learning model. What does it mean for a model to be good? How do we measure that? And why is there not just one number that tells us the answer? You have probably heard of accuracy. You have probably heard of precision and recall. F1 score, AUC, R². They all claim to tell you how good your model is. But here is the strange thing. For the same model, on the same data, these metrics can disagree wildly. One says 99% excellent, another says completely broken. Both are correct. They are just answering different questions. The reason there is no single best metric is statistical. A machine learning model produces a stream of predictions. Each prediction is either right or wrong, or off by some amount. The collection of all error forms an error distribution. A metric is just a statistic that summarizes this distribution, like a mean or a variance summarizes a sample. Different summaries highlight different aspects of the same data. By the end of this video, you will know the most important metrics: accuracy, precision, recall, F1, ROC, AUC for classification, and MAE, RMSE, R² for regression. More importantly, you will know how to pick the right one for your problem, because the wrong metric can hide a useless model behind an impressive looking score, and the right metric can save you from shipping something that fails the moment it hits the real world. We will cover the math, the geometry, and a worked example for every key matrix. Now let us begin. Before we look at any specific metric, let us understand what a metric actually is. Statistically speaking, a trained model takes an input and produces a prediction. We compare that prediction to the truth. The difference between the two is an error. For a classification model, the error is binary. The prediction was either right or wrong. For a regression model, the error is a number. The prediction was off by some amount. If we run the model on 1,000 test examples, we get 1,000 errors. This is the error distribution. It has a shape, a center, a spread, and tails. It is a random variable like any other. A metric is a statistic that summarizes this error distribution. Accuracy summarizes it by counting the fraction of 0 errors. Mean squared error summarizes it by averaging the squared values. F1 score takes a particular ratio. R² compares it to the variance of the targets. Different statistics emphasize different aspects. The mean tells you the average. The median tells you the typical value. The standard deviation tells you the spread. None of them is the data. Each one is a lossy compression. The same is true for evaluation metrics. Each one throws away information to give you a single number. This is why different metrics can disagree on the same model. They are not contradicting each other. They are simply summarizing different aspects of the error distribution. Once you see this, the choice of metric becomes a real question. Which aspect matters for my problem? For classification problems, every metric you have ever heard of is built from one foundational object, the confusion matrix. It is just 4 numbers. Imagine you are building a spam filter. The model looks at an email and predicts spam or not spam. The truth is either spam or not spam. Combining the prediction with the truth gives you 4 possible outcomes. True positive, the model said spam and it was actually spam. We got a real spam email. Now false positive, the model said spam but it was actually a normal email. We blocked something important here. True negative, the model said not spam and it correctly was not spam. We let a real email through. False negative, the model said not spam but it actually was spam. We missed it and the user sees a phishing message in their inbox. Now arrange these 4 counts in a 2 by 2 grid and you have the confusion matrix. Let us run a concrete example. Say we test a filter on 100 emails. 20 are actually spam, 80 are normal. Our model flags 15 emails as spam. 12 of those flagged emails were actually spam. That is 12 true positives. 3 were normal emails that got blocked. 3 false positives. Of the 85 emails the model said were normal, 77 actually were. 77 true negatives, and 8 were spam that we missed, 8 false negatives. 12 plus 3 plus 77 plus 8 equals 100. Every test example is in exactly one box. From these four numbers, 12, 3, 77, 8, we can compute every classification metric you have ever heard of. Now the simplest metric is accuracy. Accuracy equals the number of correct predictions divided by the total number of predictions. In confusion matrix terms, TP plus TN divided by the total. For our spam filter, accuracy equals 12 plus 77 divided by 100. That is 89%. Sounds great. The model is correct 89% of the time. But here is where accuracy starts to lie. Imagine a different problem. You are screening patients for a rare cancer. Suppose only 1 in 1,000 people in our population actually have it. If you build a model that simply predicts no cancer for every patient, never flags anyone, you will be correct 999 times out of 1,000. Your accuracy is 99.9%. That sounds spectacular, but the model is completely useless. It has never identified a single cancer patient. Every actual cancer case has been missed. This is the accuracy paradox. When your classes are imbalanced, when one outcome is much rarer than the other, accuracy can be misleadingly high, while the model fails the only task that matters. And imbalanced data is everywhere in the real world. Fraud detection, rare disease screening, manufacturing defect identification, network intrusion alerts, customer churn for healthy companies. In all of these, the positive class is rare. Accuracy treats every example as equal and lets the rare cases get drowned out. So we need metrics that look at the rare cases specifically. That is where precision and recall come in. Precision and recall ask two different questions about the model's predictions. Each one focuses on the rare class, the positive class, and asks a specific question about it. Precision asks, of all the times the model said positive, how often was it right? In confusion matrix terms, precision equals true positives divided by true positives plus false positives. It is the model's hit rate among its flagged cases. Recall asks, of all the actual positives in the data, how many did the model catch? In confusion matrix terms, recall equals true positives divided by true positives plus false negatives. It is the model's coverage of the real world positive cases. Let us compute both for our spam filter. 12 true positives, 3 false positives, 8 false negatives. Precision equals 12 divided by 12 plus 3, that is 12 over 15, equals 80%. So when the filter flags an email as spam, it is right 80% of the time. Recall equals 12 divided by 12 plus 8, that is 12 over 20, equals 60%. So of the 20 actual spam emails, the filter caught only 12. 40% slipped through. Now here is what nobody tells you when you first learn these. Precision and recall trade off against each other. You can crank precision up by being very conservative. Only flag emails you're absolutely certain are spam. But then you catch fewer of them, recall drops. Or you can crank recall up by flagging anything remotely suspicious, but then you block lots of normal emails, precision drops. This trade-off is geometric. As you move the decision threshold of the model from strict to lenient, precision falls and recall rises. There is no free lunch. You cannot maximize both unless your model is essentially perfect. Which one matters more depends on your problem. For cancer screening, you want maximum recall. Better to flag too many and follow up than to miss a case. For sending automated legal notices, you want maximum precision. Sending a notice to an innocent person is a much bigger problem than missing one guilty person. So now you have two numbers, precision and recall. That can disagree. Sometimes you want a single number that combines both. That is the F1 score. F1 is the harmonic mean of precision and recall. Specifically, F1 equals 2 times precision times recall divided by precision plus recall. Why harmonic mean and not arithmetic mean, you might ask, right? Because the harmonic mean punishes imbalance. If precision is 100% but recall is 1%, the arithmetic mean would be about 50%. Sounds okay. But the harmonic mean would be about 2%, correctly telling you the model is broken. The harmonic mean is dominated by the smaller of the two values. If either precision or recall is small, F1 is small. You cannot get a high F1 by being great on one and terrible on the other. For our spam filter, precision 80%, recall 60%. F1 equals 2 times 0.8 times 0.6 divided by 0.8 plus 0.6. Numerator 0.96, denominator 1.4. F1 equals 0.686 or about 69%. Now sometimes the two sides should not be weighted equally. If recall really matters more than precision, say for cancer screening, you use a generalized version called F beta. F beta equals 1 plus beta squared times precision times recall divided by beta squared times precision plus recall. When beta is greater than 1, you are weighing recall more. F2 is a common choice for medical screening. Recall is twice as important. When beta is less than 1, you are weighing precision more. F0.5 is used in things like spam filtering when you want to avoid false alarms. There is one more classification metric you must know. ROC-AUC, Receiver Operating Characteristic Area Under the Curve. Here is the problem it solves. Every metric we have looked so far, accuracy, precision, recall, F1, depends on a decision threshold. The model outputs a probability or a score and we say if it is above 0.5, call it positive. If we change that threshold, the confusion matrix changes and every metric changes with it. So how do you evaluate a model without committing to a single threshold? We sweep across all possible thresholds and see how the model performs at each one. At each threshold, we compute two quantities, the true positive rate, same as recall, and the false positive rate, false positives divided by the total actual negatives. As we move the threshold from very strict to very lenient, both rates change. We plot the false positive rate on the x-axis and the true positive rate on the y-axis. The resulting curve is the ROC curve. A perfect model has the curve hugging the top left corner, 0 false positives, 100% recall. A random guess gives a diagonal line, same true positive rate as false positive rate. The closer your curve is to the top left, the better. AUC, area under the curve, summarizes the whole curve into a single number. A perfect model has AUC equals 1. A random model has AUC equals 0.5. A practical interpretation, AUC is the probability that the model ranks a random positive example higher than a random negative example. An AUC of 0.8 means there is an 80% chance the model gets the ordering right. AUC is threshold independent, which makes it great for comparing models, but it has a known weakness. On highly imbalanced data, AUC can look impressive even when the model is not actually useful. For imbalanced problems, the precision recall curve and its area, PRAUC, are often better suited. So far, we have looked at classification, discrete yes or no predictions, but many models predict continuous numbers, house prices, patient blood pressure, tomorrow's rainfall. For these regression problems, we need different metrics. There are 3 you must know: mean absolute error, mean squared error and its cousin root, mean squared error, and R squared. Mean absolute error, MAE for short. Take the absolute value of the error on each example, then average across all examples, and MAE equals 1 over n times the sum over I of the absolute value of yi minus y hat I. It tells you the average size of your prediction errors in the same unit as the target. Mean squared error, MSE. Same idea, but square the errors before averaging. MSE equals 1 over n times the sum of yi minus y hat I squared. Because we squared, large errors get penalized much more heavily than small ones. An error of 10 contributes 100 to MSE. An error of 1 contributes only 1. RMSE is just the square root of MSE, bringing the unit back to the original scale of the target. Most people report RMSE rather than MSE in practice. Here is the key difference. MAE is robust to outliers. Each error contributes proportionally to its size. RMSE is sensitive to outliers. A single large error can dominate the entire score. Which one do you want? Depends on whether large errors are catastrophic or just unfortunate for our problem. Then there is R², the coefficient of determination. R² equals 1 minus the sum of squared errors divided by the sum of squared deviations from the mean. It compares your model to a baseline that just predicts the average. R² equals 0 means your model is no better than predicting the average. R² equals 1 means perfect fit. R² can also go negative, meaning your model is worse than just guessing the mean. R² is unitless, which makes it easy to compare across problems, but it has its own quirks. Adding more features always increases or maintains R², even if those features are noise. For comparing models with different number of features, use adjusted R², which penalizes extra parameters. Now that we have 10 metrics on the table, the practical question is, how do you pick the right one for your problem? 4 questions asked in order. Question 1. Classification or regression? If your target is discrete categories, you are in classification. Use accuracy, precision, recall, F1, AUC. If your target is a continuous number, you are in regression. Use MAE, RMSE or R². Question 2. For classification, are the classes balanced or imbalanced? Roughly 50-50? Use accuracy or F1. Heavily skewed, say 1 to 99, avoid accuracy. Use precision and recall. F1, PRAUC. Question 3. What is the cost asymmetry of false positives versus false negatives? If false negatives are catastrophic, like missing a cancer case, maximize recall, use F2. If false positives are catastrophic, like wrongly flagging a transaction as fraud and freezing an innocent customer's account, maximize precision, use F0.5. Now question 4. For regression, are outliers part of the signal or unwanted noise? If outliers matter, like predicting peak electricity demand, use RMSE. If outliers are just noise, like average house prices, MAE is more honest. Apply this framework consistently and you will avoid the most common failure mode in machine learning, shipping a model that scores well on the wrong metric and fails on the actual job. Now let us put everything in one reference card. 8 metrics, 5 for classification and 3 for regression, plus the meta rule. Now screenshot this. Classification, accuracy equals TP plus TN over total, easy, lies on imbalanced data. Precision equals TP over TP plus FP. Of your positive predictions, how many were right? Use when false positives are costly. Recall equals TP over TP plus FN. Of all the real positives, how many you got? Use when false negatives are costly. F1 equals 2 PR over P plus R. Harmonic mean of precision and recall. Use for a single balanced number. AUC, area under the ROC curve, threshold independent ranking quality, used to compare models. Regression, MAE, average absolute error, robust. RMSE, square root of average squared error, outlier sensitive. R², variance explained relative to mean baseline. Meta rule, written across the bottom, the best metric is the one whose cost align with your real world failure model. Pick accordingly. So to recap, every evaluation metric is a statistic that summarizes the model's error distribution. Different statistics highlight different failure models. There is no universe best metric. For classification, accuracy is fine for balanced data but lies on imbalanced data. Precision and recall ask asymmetric questions about positive predictions. F1 combines them with a punishing harmonic mean. AUC sweeps across thresholds for a single comparison-friendly number. For regression, MAE is robust to outliers. RMSE is sensitive to outliers. R² compares to a mean baseline. The right metric is the one whose definition of error aligns with what costs you most in the real world. Cancer screening, recall. Legal acquisitions, precision. Peak power demand, RMSE. Daily temperature forecast, MAE. Pick deliberately. Document your choice, and next time someone tells you their model is 99% accurate, ask the right follow-up question. Accurate at what?